In this session, we'll cover business drivers for analytics, current analytical architecture, business intelligence versus data science, and drivers of big data and new big data ecosystems. Today, organizations contend with several business problems where they have an opportunity to leverage advanced analytics to create competitive advantage. Rather than doing standard reporting on these areas, organizations can apply advanced analytical techniques to optimize processes and derive more value from these typical tasks. The first three examples listed in this slide are not new problems. Companies have been trying to reduce customer churn, increase sales, and cross-sell customers for many years. What's new is the opportunity to fuse advanced analytical techniques with big data to produce more impactful analysis for these old problems. Business intelligence focuses on using a consistent set of metrics to measure past performance and inform business planning. This includes creating key performance indicators that reflect the most essential metrics to measure your business. Predictive analytics and data mining refer to a combination of analytical and machine learning techniques used for drawing inferences and insight from data. These methods include approaches such as regression analysis, association rules, also known as market basket analysis, optimization techniques, and simulations. For example, Monte Carlo simulation to model scenario outcomes. These are more robust techniques for answering higher-order questions and deriving greater value for an organization. This graphic portrays a typical data warehouse and some of the challenges that it presents. For source data to be loaded into the enterprise data warehouse, data must be well understood, structured, and normalized with the appropriate data type definitions. As a result of this level of control on the EDW, shadow systems emerge in the form of departmental warehouses and local data marts that business users create to accommodate their need for flexible analysis. These local data marts don't have the same constraints for security and structure as the EDW does, and allow users across the enterprise to do some level of analysis. Once in the data warehouse, data is fed to enterprise applications for business intelligence and reporting purposes. These are high-priority operational processes, getting critical data feeds from the EDW. At the end of this workflow, analysts get data provisioned for their downstream analytics. Since users cannot run custom or intensive analytics on production databases, analysts create data extracts from the EDW to analyze. Lastly, because data slowly accumulates in the EDW, due to the rigorous validation and data structuring process, data is slow to move into the EDW, and the schema is slow to change. EDWs generally limit the ability of analysts to iterate on the data in a separate environment from the production environment, where they can conduct in-depth analytics or perform analysis on unstructured data. Today's typical data architectures were designed for storing mission-critical data, supporting enterprise applications, and enabling enterprise-level reporting. These functions are still critical for organizations, although these architectures inhibit data exploration and more sophisticated analysis. Key-value databases are simply those databases where data is stored and retrieved by a unique key, usually treated as an uninterpreted string of bytes. Associated with each key is a value. Again, the values contained in this data store may be in any format, and may differ for each key-value pair. NoSQL is a label that has been applied to databases that do not necessarily use SQL or structured query language to access the data. It can also mean not only SQL, which implies that other forms of queries can be used against the data. Everyone and everything is leaving a digital footprint. This graphic provides a perspective on sources of big data generated by new applications and the scale and growth rate of the data. These applications provide opportunities for new analytics and driving value for organizations. The data comes from multiple sources. The big data trend is generating an enormous amount of information that requires advanced analytics and new market players to take advantage of that information. Organizations and data collectors are realizing the data they can collect from you is really very valuable, and a new economy is rising around the collection of data, because data is streaming off all of these computing and network devices. Consider this example. Item 1 portrays data devices and the sensor net that is collecting data from multiple locations and is continuously generating new data about this data. For each gigabyte of new data you create, a petabyte of data is created about that data. Data collectors include entities that are collecting data from the device and users. This can range from your cable TV provider tracking the shows you watch, to retail stores tracking the path you take, pushing a shopping cart in their store with a radio frequency identification chip, so they can gauge which products get the most foot traffic. Data aggregators make sense of the data collected from the various entities from the sensor net, or the Internet of Things. These organizations compile data from the devices and usage patterns, and choose to transform and package these data as products to sell to list brokers, who may want marketing lists of people who may be good targets for specific ads. At the outer edges of this web of the ecosystem are data users and buyers. These groups directly benefit from the information collected and aggregated by others in the data value chain. Big data projects carry with them several considerations that you need to keep in mind to ensure this approach fits with what you're trying to achieve. The analytic techniques being used in this context need to be iterative and flexible due to the high volume of data and its complexity. These conditions give rise to complex analytical projects that can be performed with some latency, or by operationalizing these analytical techniques using a combination of advanced analytical methods, big data, and machine learning algorithms to provide real-time or near-real-time analysis, such as recommendation engines that look at your recent web history and purchasing behavior. Additionally, to be successful, you'll need a different approach to the data architecture than what is seen in today's typical EDWs. Analysts need to partner with IT and DBAs to get the data they need within an analytic sandbox, which contains raw data, aggregated data, and data with multiple kinds of structure. Big data analytics has been used across multiple industries, including healthcare, reducing the cost of care, public services, preventing pandemics, life sciences, genomic mapping, IT infrastructure, unstructured data analysis, and online services, social media for professionals. Let's consider two of these in more detail. In the case of healthcare, Dr. Jeffrey Brenner at Rutgers University generated his own crime maps from medical billing records from 3 hospitals. He was motivated to do so after observing poor police response and problems with medical care associated with the shooting of a Rutgers student. By utilizing data collection and visualization, Dr. Brenner determined that the city hospitals and ERs were providing expensive but low-quality care. The story of LinkedIn reflects an opportunity to create a social media space for professionals. LinkedIn now collects and analyzes data from over 100 million users. The site adds 1 million users per week. Via this analysis, LinkedIn is able to offer valuable services, such as LinkedIn Skills, InMaps, job recommendations, and recruiting. Since LinkedIn's founder is convinced that data analytics is the wave of the future, LinkedIn has gone so far as to establish a diverse group of data scientists.